So good afternoon, everyone. So first of all, I want to say it's a pleasure to be here and share with you some work that we've been doing in the last 4 or 5 years, trying to take pure water to the poor. I'm a professor at Princeton, and a lot of my work in nanotechnology tends to be rather esoteric, you know, very sort of looking at the future 20, 30, 50 years from now. And having grown up in Nigeria, a developing country, I started to think a little differently about how one might do nanotechnology that could impact the lives of people. And in thinking about this, I was motivated by the following problem. If you look at most villages in the developing world, you find that most people drink water that comes from places like this. They defecate in the same water. They wash in the same water, and 20% of all the children in those countries will die before the age of 5. And an even more sobering bit of statistics is that when I was a boy in the 60s, the life expectancy in my home country of Nigeria was 65 for women and 63 for men. Today, the life expectancy in the same country is 45 for women and 43 for men, and going down, which sort of means that I actually should be dead. It's very sobering. Now, if you actually then look at what's really responsible for this steep decline, it turns out it's not HIV. The HIV infection rates are very low, much less than 5%. And it's not malaria, tuberculosis, so many of the things that get the press. What actually happens is that if you drink water like that, as a child, without your system being well developed, you can't fight the bugs. Effectively, you'll see in some villages, all the kids have permanent diarrhea. And in the case where they get typhoid, they often think this is malaria, until it lacerates the intestines. And as you go through your life, you get exposed in different ways to this water. So the mortality figures collapse. So motivated by this and the fact that you lose roughly 5,000 lives a day, that's about 1 trade center per day, to problems of contaminated water, I started to think about what the potential solutions might be. Now, if you say, well, why not just install more central generation for purification of water? The problem with that is that the pipes are cracked. So somewhere along the way, the water gets contaminated. If you actually talk to the people that manage the pipes, what they do is they add a little bit more chlorine, which basically means if you live close to the waterworks, you're drinking a lot more chlorine than you should be. And if you live far away from the waterworks, you're drinking a lot more bugs than you should be. So the real issue then is, how do you make sure that the water that people drink at the point of use is clean? That's the first thing. Then the second thing is, how do you make sure that this is a sustainable solution? For this to be sustainable, it has to be a solution that goes on long after the financial intervention is made. So there has to be a way in which people make a living and have an incentive to keep this going, even after the initial establishment of some support structure that creates the solution. So we started thinking then, what are the potential solutions that can give point of use purity of water, and how can we do this so that it's applicable to rural areas so you don't have to import anything, and then how do we do this so that it continues on long after the intervention is made? So you have to have some entrepreneurship or social entrepreneurship strategy that's built in to keep this going. So if you look at the alternatives, you might say, well, boil the water. The problem with that is that you end up, in some senses, creating a situation that's not often practical. You might add chlorine, but chlorine is not always available, even to the waterworks. And so that's not a solution, especially in the rural areas. Or perhaps you might do solar disinfection, which basically means putting the water in bottles and pasteurizing at about 40 to 50 degrees. That works, but it's a bit of hit and miss. On days when you don't quite get up to temperature, you end up with some bugs in the water. Or you may have a biosand filter, which has a combination of sand filtration and big bugs basically eating little bugs. If you don't optimize that layer quite well, the Schematic layer, you end up with some problems. Or you might have this ceramic water filter that I'm going to talk about, which can filter out microbes in a way that makes it accessible, but not necessarily filter out chemicals. And then lastly might be our Procter & Gamble filter that costs $100 or $200 that nobody else can afford. So when you look at that, you realize that many of the solutions are not really viable. So in thinking about the potential solutions, I met a pioneer in this area called Ron Rivera. And Ron had been working with some scientists from Latin America on a ceramic water filter known as Filtron, where essentially what they had was a filter that's made out of clay and sawdust, that's processed from materials that are locally available in almost every country. And the basic principle is fairly simple. This, although it looks solid, is 50% porous. And when you pour contaminated water into it, this essentially filters out the water. The way that this works is that we have within this structure that can provide enough drinking and cooking water for a family of 4, enough volume of water for them to consume. And within the structure itself, although it looks dense from the outside, you have these pores that are both micro and nano porous in size. So you have a bimodal distribution of pore sizes that you can control by controlling the sizes of the particles that you sinter in the process. Now, the way you create the pores is by mixing sawdust and clay together. You can get the sawdust from almost anywhere. You can sieve the sawdust to the sizes that you want, and those essentially blow little bubbles into the material in ways that occlude the pathogens. So it turns out that from this very simple idea, you can now begin to build the science around filtration. So what you really want to do is you want to create a structure that essentially occludes, disinfects, and potentially also adsorbs. That's the basic ideas. So if I imagine now a pathogen, this pathogen can be some kind of a microbe, and if you want to imagine how big a microbe is, for many of you, if you put your hands on your heads and you pick out a strand of hair, that's about 100 microns in diameter. And in my case, if I move to the front here and I pick out another strand that you can't see, that's on the nanoscale, right? So clearly, at that scale, if you take 1/10 of that, that's 10 microns. 1/100th of my hair diameter, that's a micron. At about a micron, you can basically filter out all the microbes, bacteria, E. coli, all those things that cause potential problems. And the way it works is as follows. So the first thing that happens is the microbes get trapped when you control your pore sizes. And once they get trapped, then the rest of the water flows through, and that keeps the water pure. The problem with this, though, is that they can then start to multiply. So you need a way of essentially killing the bugs. And if you look closely in gray, you'll see that I've introduced some kind of a coating. This coating can be some kind of a bactericidal coating. You can use copper, you can use silver, and interestingly enough, you can synthesize these with bugs, which is quite intriguing. And so you can now create these coatings that you introduce by dipping, and as the pathogen goes through, you have an electrochemical interaction that disinfects the water. So you have 2 ways then of killing the bugs. So one is the trapping mechanism, and then the second one is this electrochemical interaction, and the combination of the 2 of them basically give you pure water. You can do this in almost any environment where you can create these porous structures, and I just want to illustrate some of the ways in which you can do this and a little bit of the science. So the first thing is, if you want the water to flow through, you need about 50% porosity with percolating porosity. Essentially, the pores must all connect so that as the water flows through, you can go from one point to the other. And so if you play with the different volume fractions of pores, you find it's roughly about 50 volume% porosity. Now, the other thing that you might do, and I promise you I'll only show 2 roughly technical slides, is you might try to understand the flow And if you have nothing better to do at Princeton, you can watch these droplets as they come out. And you can try to understand them. And what you can essentially show is that as you increase the porosity, the flow rate increases. But if the flow rate, of course, exceeds a certain amount, you end up with a situation where you let the bugs out. And so we started to understand this. We basically can show that this is Darcy flow, except for the very beginning, where you have to establish steady state conditions. And you can go through the math. Essentially, the flow goes through the base, and you can basically assume Darcy flow through the base. The flow goes through the sides, and you can integrate up the sides, and the total flow is the sum of the flow through the base and the flow through the sides. So from that, you can then work out your total volumetric flow, and you can essentially show that your total flow in terms of the description of that flow can be done by a single permeability. The only time this doesn't work is when you have to establish steady state at the beginning of flow. Now, beyond that, you can remove most of the microbial pathogens. So because the pore size is generally a micron or greater, we can filter out E. coli, we can filter out protozoa, multicellular organisms. And the net result of all of this is that we end up with water that basically removes 99.9% of the microbes. So this is pretty encouraging. Now, that's stuff you can do in the lab. Now the real question is, can you go from the lab to a real factory? And can you make that factory sustainable? And there are many colleagues, including many at Princeton and many universities, often we think, oh, we've done this, therefore it is. And so we started to look at ways in which you might do this out in the field. And this is a group in what used to be South Darfur, now Southern Sudan, where a group of women started to make the filters. And so they learned about the technologies. They could actually fabricate the filters. And then they could use local kilns that they built. And not only could they then do that, they can dip in colloidal silver to make these disinfect the water. And then they set up intricate schemes. You know, they have rates for their friends, rate for their distributors, rate for the market. And they set up a sustainable enterprise. And so motivated by this, we started to think of how do you go from ideas to markets? And could we really do this in a way that's sustainable? And that led us to establishing a factory in the town of Abeokuta, which is actually my hometown in Nigeria. And this was started using a very different approach to creating a factory. So normally when people create these factories, you import all the equipment, you bring all the expertise from outside, and you don't necessarily utilize the knowledge of the local people. And so we decided that we would get a bunch of local clay workers and woodworkers that know about sawdust and wood, and bring them to work with us and merge our own knowledge from the research that we had done into the establishment of a factory. We also decided, working with a group of Princeton students, that we would do this without importing all this equipment from outside, but we would build everything from the ground up and set this up in a way where it would have the governance and it would have a structure that hopefully over time would sustain itself. This town, by the way, which is produced 3 Nigerian presidents, if you go 20 minutes from this town, you find that the water is highly contaminated, and I'll show you some of that. So we worked with Potters for Peace and Ron Rivera, who was the head of Potters for Peace, a local university, in establishing this factory. And we paid a lot of attention to trying to establish quality control in a rural setting, which is non-trivial. And so this took a year to really inculcate this culture in a way that the folks in the factory recognized. Once the folks in the factory could actually work with clay to make filters, it turns out that they also had the skills to make building blocks, roof tiles, and other materials. And so they could use these new skills as ways of generating some additional income when they didn't have filter supplies. And so it's interesting that from a simple idea like this, you build other skills that you can refine over time. They also, by the way, became a place where we can do research in the field. And we have since developed filters that can remove not only microbes, but viruses, as well as chemicals. And the nice thing about it is once you develop the idea in the lab, they can produce it in the field. And from there, we've exported to Haiti, we've exported to Kenya and Burkina Faso, the filters that they've produced. Now, in thinking about this, it's kind of interesting to really realize that one of the key things you have to do is you have to have a robust marketing strategy. Because often, if you don't think about a local, global marketing strategy, these activities are not sustainable. So thinking about how you appeal to rural and urban communities, local schools, NGOs, hospitals, clinics becomes part of really thinking through how you market these concepts. And from a small town in Abeokuta, you can actually supply the world. If you have the right distribution and marketing strategies, you can do a lot. And simply also from that small town, you can train others in other places to start the factory. And so we've been working to try to develop these marketing strategies into more robust ones. We need to establish closer collaborations with NGOs who are great vehicles for doing the distributions. And we're also thinking about how to scale up from this initial point to a point where there might be a network of factories where local people train each other in ways that establish quality control and marketing and distribution networks, and reach out to both rural and urban populations in ways that are different. It turns out that people are not only concerned, by the way, about removing the bugs, but how the filters look. And so you have to put quite a lot of effort into developing the right kind of aesthetics as well as removing the bugs. Now, I just want to show you that you can do this not only for the shape of filter that I've shown, but for a range of filter shapes. And so we've actually been modeling, these are symmetry type things, so we're showing only half of the shape. All the possible types of filter shapes that you could imagine. Looking at where the stress concentrations are and optimizing the shapes in ways that now allow us to think about scaling up the volume of filtration as well as changing the shapes in ways that might be optimal. So it's kind of interesting. You can connect the research then directly to the production in ways then that allow us to think about serving not just small communities but larger communities. You can also think of ways of stopping the clays from breaking. You basically can look at cracking and how these things can crack along the sides and the base. It turns out that the key there is making the clay itself self-reinforcing, where particles in there can resist cracking by resisting the opening of cracks due to loading of the structure. So we're applying techniques really that were used to develop tough materials for aerospace materials to improve these materials for the poor. Now, you can do all of this, but the real question is, do you really impact public health? And because you can say, well, you remove all the bugs, but that doesn't prove that the health and well-being of the people is improved. And so what we did was then to do a questionnaire study where we looked at the health and well-being of the people before the filters were introduced, and then 6 months afterwards, and up to a year afterwards. And it's interesting to do this kind of work where you team up with local doctors, you team up with local folks at the universities, and you begin to develop a database and some understanding of the potential impact that this can have. So this is the village we chose. It's called Eweje, which is just on the outskirts of Abeokuta. This is the water that people drink in this village. It's very sobering, because this particular town was the first town that had contact with Western missionaries. And so it has a lot of very educated people. We have one Nobel Prize winner, Wale Soyinka, that lives within 20 minutes of this place. And this is the water that people drink. Now, if you now look at where they wash their pots and where they bathe and where they defecate, it's the same water. So as a result of this, they get sick. Now, ultimately, if you do the measurements of people's health indices and well-being, and you then look at the changes in 6 months, you see that in 6 months, you basically eliminate dysentery, typhoid, and diarrhea. but you have to back it up with education. Because what happens is that, let's say you go in and you find the chief, he says, oh, we're so happy to see you guys. I feel very strong. We say, where's your filter? He says, it's under my bed. Why is it under your bed? I don't want anybody to be stronger than I am. So you have to say, well, chief, you need to set a good example. And in that case, you of course have to provide 1 or 2 more filters for other people in the house. That's the solution. And then you go see somebody else. There's a woman for whom this is her most prized possession. And you say, well, how's the filter? Oh, it's just wonderful. I'm so happy to have this. But it's beginning to get dirty. So I don't want it to get dirty, so I'm going to start drinking dirty water and keep it clean. And you say, no, you have to clean it. You have to clean it this way. And you have to monitor this in a way that allows this to become part of their way of life. And in fact, interestingly enough, now we're about to go into the next phase. We just published a paper on this earlier on in the year. We're about to go into the next phase to really look at what it would take, not only to do this in this village, but to diffuse this across other places. So we think that there are lots of implications. One, it shows that you can improve the health and well-being of people. You need to have education to avoid misconceptions. You also, in some senses, need to have some ratio of filter to number of people in the house to make sure that everybody has access to clean water. And we have to think about scale up. This is just a small experiment. And so we're now working on what we call a franchise model, where we want to take this experience to create other such factories across different regions and use this as a way of diffusing the technology to other places. We also want to involve the poor in the diffusion of those technologies so that they become part of a solution in a way that can propagate this beyond where we are. And then most recently we've been thinking about marketing and entrepreneurial research. There's a spelling mistake there. We're also thinking about ways of doing research to address other problems of water, such as fluoride, arsenic, and heavy element contamination. It turns out you can dope the clays in ways that increase the absorbance of these contaminants. And we've already done the experiments to show that this happens. So it's now a case now of translating those into real-world applications, public health policy, as well as entrepreneurship strategies. So we think that when you combine then this whole notion of doing research with working with the poor in the field, and you connect to real markets through social entrepreneurship or entrepreneurship strategies, you can then produce the vehicles through which you can have sustainable introduction of technological solutions to the problems of the poor. And as we started that, we've now reached out to Burkina Faso and Kenya. We've already started working in Burkina Faso, where we've transferred the press technology. And we've already started working in Kenya this summer, where we're now introducing the filters actually produced in Nigeria. And then we're working with other universities to expand this within the vehicle, where students in universities also begin to learn about solutions, working in partnerships with Princeton students and other students. And we're now at the beginning of an effort to think of how best to create a social franchise strategy that would diffuse this technology across Africa and perhaps other parts of the world. So in conclusion, I hope that I've been able to convince you that this holistic approach from ideas to markets is a way of really thinking through solutions to problems of water purification. The way we purify is by geometric occlusion through the pores, which are both nano and micro scale pores. The colloidal silver disinfects the water. We've also shown recently, by the way, that copper does the same thing, which is why copper was used in old door handles. And we're now working with copper as an alternative to silver. It turns out you can synthesize these nanoparticles using bacteria. And so we're now using bacteria to synthesize nanoparticles from local salts, and showing that you can also create the solutions from the things you're trying to trap. We've shown that these things are mechanically robust, and we can use local materials to make them even more robust. But the most challenging, actually, was trying to figure out what it takes to create a sustainable enterprise from local people that achieves the right levels of quality and also engages the community in ways that actually helps to create the solutions to the problems that they have. But we feel that we need to have more of this and we therefore need greater diffusion of technologies. So I just want to thank the people that have done the work. This has been a remarkable effort from many, many folks across different continents, students, faculty members, collaborators, doctors that have worked, and I've simply just tried to represent their activities in a short presentation. Thank you.